Hello everyone, my name is Rungrat Viratikul from the Department of Electrical Engineering, Faculty of Engineering, Chulalongkorn University. Today, I am going to present the topic called Investigation of Electromagnetic Mode Transition in 220 to 325 GHz Horn-type connector. Okay, without further ado, let's get started. Start with the introduction part. Terahertz technology has emerged as a promising field, diverse application in communications, imaging, spectroscopy, and sensing. The efficient transmission of terahertz signals is of great importance for numerous applications. The successful operation of terahertz system is highly dependent on the proper design and optimization of the waveguide components. Among these components, a connector between waveguide sections play a crucial role in facilitating the transition between different electromagnetic modes. Therefore, this research presents a comprehensive investigation of electromagnetic mode transition in a terahertz horn-type connector. The main objective of this research is to gain insight into the mechanism of mode conversion within the horn-type connector and to evaluate the factors that influence the mode conversion process. Let's move to the design of the horn-type connector part. As we know, different waveguide modes can occur in a horn connector depending on the geometry and dimensions of connector. The specific modes in a horn-type connector are determined by the transition from one guide to another. The design aims to provide efficient mode transition and low insertion loss while maintaining a specific mode. In this case, the TE10 mode of the WR3 rectangular waveguide with vertical polarization. The TE10 mode represents the fundamental mode of the rectangular waveguide and serves as the input mode for the horn-type connector. To design a horn-type connector, the CST Microwave Studio Suite was used to study and optimize some key parameters to improve its overall efficiency. These two figures show the longitudinal and cross sections of the horn-type connector. Also, the figure illustrates the proposed horn-type connector fabricated by CNC milling. Besides, the geometric parameters of a horn-type connector for efficient mode transition from a TE10 mode of the WR3 rectangular waveguide are listed in the table. As shown in this figure, the electronic-based terahertz measurement setup comprises the setup of a horn-type connector integrated system. Two high-frequency extenders operating from 220 to 325 GHz are connected to a network analysis to ensure the terahertz test signal transmission and receiving are sent, received, and analyzed. The terahertz beam emitted from the WR3 rectangular waveguide at the transmission extender is fed into the input port of the horn-type connector. It converts the TE10 mode with vertical polarization in the WR3 rectangular waveguide into the dominant TE11 mode with vertical polarization and the other competing modes in the horn-type connector as well. A horn-type connector can be used for efficient mode coupling between different waveguides, which is typically designed to convert the mode profile of a given waveguide, for example, the black fiber to match the mode profile of another waveguide or optical devices. In the figure A and B, a WR3 rectangular waveguide is connected to port 1 of a horn-type connector. The TE10 mode with vertical polarization of port 1 exhibits mode conversion. It is predominantly converted to TE11 mode with vertical polarization within the horn-type connector. As shown in figure C, in addition to figure D to F show three other competing selective modes. namely TE11 mode with horizontal polarization, TM01 mode and TE21 mode, which are also selectively represented at port 2 of the horn type connector. Okay, and this figure shows the proposed measurement setup using a horn type connector attached to the WR3 holometric rectangular waveguide, aka HMRW, and the black fiber fixed securely on the sample holders. Okay, let's move to the simulation results and discussion. This figure shows the simulation results of insertion load, aka S21 and S12 of the 4 selected representative modes. The result indicates that S21 and S12 are characteristically identical for the same modes, which proves that the horn type connector has the reciprocal property. For TE11 mode with vertical polarization, the insertion loss is nearly zero in both directions, indicating that the TE11 mode with vertical polarization at port 2 is well matched to the TE10 mode with vertical polarization at port 1 as well. This compatibility ensures a smooth transition and efficient mode conversion within the horn type connector, and the benefit of near zero insertion loss of the TE11 mode with vertical polarization contributes significantly to improve performance and reliable transmission in terahertz application. And more importantly, the design and optimization of the horn type connector. The dimension and shape of the horn must be carefully designed to support and ensure the desired mode, reduce mode, and protect from the other unwanted modes and minimize power loss. Okay, let's move to the conclusion. As I bring my presentation to a close, I want to take a moment to summarize the key takeaways that I have explored today. This research presents a thorough investigation of the electromagnetic mode transition in horn type connector for the frequency range of 220 to 325 GHz. The investigation was carried out by numerical simulation using CST Microwave Studio Suite, and the main objective of this investigation is to design a horn type connector that can provide efficient mode transition from a TE10 mode of AWR3 rectangular waveguide to a desired mode, and the result showed the mode conversion from a TE10 mode of AWR3 rectangular waveguide in the horn type connector and evaluate the factor affecting the mode conversion process. Moreover, the results in the design of the horn type connector can achieve the optimal TE11 mode transition while still maintaining vertical polarization, and the TE11 mode with vertical polarization exhibits very low insertion loss. But on the other hand, the 3 competing modes, including TE11 with horizontal polarization, and TE01 and TE21 exhibit higher insertion loss, meaning that the TE11 mode in the vertical polarization is as good to be matched with the TE11 mode and TE10 mode in vertical polarization to get the best efficiency and the zero of the insertion loss. Thank you all for your attention. It's been a pleasure sharing my research with you today.